It works now? Okay. Yeah. So well, let's start saying something about what neuron models are. So, but I will not start from the definition. I have recently seen a talk by David Holmes, which I guess was also among the invited speakers but could not come, that started in a very beautiful way via examples. So let me steal this from him. So S is a regular separated scheme, and U is a dense subscheme, and well, A or E, since I start with an elliptic curve, is an abelian scheme on U. So the question is all about the question we will ask is all about extending this structure across the entire base scheme S. And so the answers to these questions are usually called models, S models. And of course, there is an abundance of models. And many talks we have seen are address the issue of finding a proper model. So the whole point today is that I will not look for a proper model. So the whole point of neuron models is that we will avoid insisting on properness, and I will insist on something else. You may say the group structure, but the real key ingredient of this definition is the smoothness. So let's take an example. So here is S to be a little disk around the origin. Say I write this, and maybe it's a bit imprecise, and I take off the origin. So E is going to be defined I said that U is the parameter of the base scheme, and so here I give affine coordinates, but all this is meant to be inside a weighted projective space across, of course, the base scheme S. So whenever you specified U, you get one of these equations that you may look at as a weighted homogeneous equation. Now notice that Y has weight 2, X has weight 1, and I have suppressed the third coordinate. But all these elliptic curves don't meet the nasty point with the stabilizer, so don't need to worry. This does indeed form an elliptic curve over U, but also suggests a completion, a model over S. Well, you see, you can take E over U, but you can consider the same equation over S. So here I actually should have started by placing this over U, but I can take the same equation over S. And I get something which is not elliptic, but a genus 1 curve. But what I would like to consider is something else than this curve. And it's a regular, it's a smooth part of this structure. Why do I do this? Well, to begin with, you have seen this picture before. Let's draw a picture of of this family of curves. If you take S and you look at it as a base parameter space where U tends to 0, here you have an elliptic curve, and down here you have a curve that looks like this. So, of course, you have a distinguished section specifying the identity element. Okay, so of course this is not a group because of the singularities. But if you remove the singularities, which is what I have done here, then you get a group. And the special fiber on 0 is nothing but 2 copies of C star, GM, union GM. And in some sense, and here I introduce the definition, this is a very good model. Here's the definition. It's due to Néron, and it has been called later Néron model. So, well, first of all, I would say the obvious things. I would start from an abelian scheme. Smooth, proper group scheme over U. And a Néron model for A on S is a smooth finite type, separated. Now I'm going to say group scheme, although you will see straight away that I could suppress these two words. And N on S, which is a model. I mean, the whole point is that we have to extend this. So the restriction on U should satisfy which with an isomorphism. And such that the following is satisfied. Okay, so here I just said that I'm taking a model. But here is the key part of the definition. What I want to do here is to say that for any smooth scheme over S, and for all U morphisms, Tu to N U, let's call them F, little f. There exists a unique S morphism, which I will call capital F, onto N, such that F restricted to Tu is equal to little f. Let's draw a picture to see if this gets clearer. So I started with A, and it was here on U. I asked the same question as before, i.e. whether there exists some model of A extending A across S. But this time, I impose the following condition. Whenever I take T to be a smooth S morphism, a smooth scheme over S, then for any morphism little f from Tu to A, there should exist a unique capital F that makes this work. So I suppose for the definition, I suppose you only have to look at this picture. And in particular, so first example 1 is an error model. Namely, and Néron model of E is indeed this. remark number 0. Remark number 2 says that even if I suppress this words group scheme here, if I suppress these words, I don't change so if I suppress without group schemes in the definition, the resulting model is a group scheme. Okay, so this is interesting in the sense that, of course, giving a group structure means giving lots of morphisms. And these morphisms all come from playing this game over and over again. Number 2, if you take T to be S itself, then you realize that instead of S, T mapping to S, I have the identity from S to itself. And then instead of this map, I have this map. And it says that every time I have a section from U to A, there is a way to extend it on N. So you know that if you have a section from S to N, there is a way to restrict it. But the point is that you can go backwards. So this gives a unique way to, I denote by this, the U points, the points mapping from U to A, are in one-to-one correspondent to the S points. Okay, so this should maybe get some, get you interested in this notion. Maybe I can only leave this as a definition of neuron model and remove this. Because all I'm going to say is that the neuron models are models, i.e. ways to extend across the points I've taken off from S, and they satisfy these universal properties. And now there is another, all this example was conceived to make you appreciate another subtle aspect of this notion. So let's take the same thing, but this time around we consider this. And this is going to be over inside the P121 as before, cross a certain U. This time S is going to be a 2-coordinate space, and U is going to be the complement of the origin, or the complement of, let's say, U equals 0 and V equals 0. Okay, so again, I have E, because I denoted it like this, is an elliptic curve. And then this is inside S. And again, I can take the same equation. And by taking the closure within the space, I can get an elliptic, genus 1 curve, stable curve. But what I'm doing here, genus 1 curve. And so what I'm doing here again is taking away the singular points. And one can wonder if this is, again, a good model. And the answer is no. How can I say this? Well, I cannot even say it in this way, because employing this notation, using this notation, amounts to say that I actually know that there always exists a neuron model. In this specific case, there is no neuron model. Okay, so what happened? Well, the first thing to appreciate here is that it's very hard to put a group structure in this scheme. And this is something I found amusing to observe. So I will replace this picture, which now you probably have looked at enough, with a picture of this family, which occurred in this first talk in the morning, I suppose. So okay, we have again this curve, which is the curve over the point u equals 0, v equals 0. And if you keep v equals 0 and let u vary, then you have a family of curves that look like this. And you keep v equals 0 and let u vary, then you have a family of curves that look like this. Elsewhere, you have a smooth curve, an elliptic curve. And now, one good way to convince yourself that this is posing problem from the point of view of the group structure is to just play with restrictions of this family along a path hitting the origin, coming from the smooth interior part, the u part, and hitting the origin. So I will draw it in another color. So let's say that this is a one-dimensional scheme, spec R, and I want it to be transversal to both this divisor and this divisor. People call this a trait in French, which is a good word, I think, because it means stroke, right? The brush stroke. So here we are looking at all the brush stroke that we can have to hit the origin. The one I'm mentioning here are all of the coordinates u equal lambda v. And what you see if you restrict on this stroke u equal lambda v, well, you see again this curve. This is going to be a regular scheme here. This is going to be regular. As a surface, it's going to be smooth over K. And you have a group structure on every fiber. And you also have a group structure which is well defined on one of the two components, it turns out, the one which contains the identity. Now, what happens for the other components? Well, the element of the other component, if you square them, get on the first component I just mentioned. So if you square any element of this component, which looks like a C star, you fall on this one. And in fact, lambda squared gets to 1. So this indicates that if I choose another lambda, I hit on another group structure. Okay? So now let's give some good news. Neural models always exist on a one-dimensional basis. And that's a theorem of Michel Renaud. And that's the first thing that we will do here. So this part of the talk is going to be if S is one-dimensional, neural models exist. Okay, so, and I'm going to do it in the case of the Jacobian. I'm going to quote this theorem of, I'm going to explain this theorem of Renaud. And so what I'm going to consider here is the case in which my S is going to be spec R. My U is going to be the spectrum of the field of fractions. And now over spec R, let me put a stable curve. And now spec k is going to be a smooth curve. Why is that? Because I want an abelian variety as a Jacobian. And I do not need to make any hypothesis on CR being regular, but I will do it, and maybe later I will tell you what happens if CR is not regular. Okay, so CR is going to be regular. So it's a stable curve, but CR is regular. And now, well, as usual, one also has the special fiber, which one denotes with a little k, and that's a stable curve. Okay, I'm mentioning it because I'm going to now need a few combinatorial things which we have seen in many talks. So as Alexiev said, what I'm going to do here is to take one of this curve and attach to it a dual graph, which we have seen many times in this conference. But I will also need a little bit of combinatorics, nothing harmful. So what I do here, I put the z-valued 0 chain, the z-valued 1 chains, okay? And since I put the indices on the upper here, I should start with the differential that goes in the right direction. But since here I have a basis, explicit basis of vertices and edges, nothing prevents me from identifying C1z to C1 with a lower index. And so I also have a differential going in this direction. These are the usual differentials of the complex of cohomology. And they are adjoined to each other with respect to some forms that say that two edges pair themselves if they are oriented in the same way, and they give as a pairing 1. So you have the structure, and I guess we are done with this. This plays a role in the proof of Renault, so I have just mentioned it here. I need a notation now. Okay, so here is a delicate part because, well, of course, so every time I write pic, I mean the pic-R group. But in a relative sense, there is a way to construct the pic-R group as a group scheme, so fiber by fiber is going to be the pic-R group. So instead of writing it systematically, I just write this. When I mean the relative pic-R group of Ck over K, which is indeed the pic-R group of Ck, and the relative pic-R group of Cr over spec R, line bundles up to pullbacks. Okay, so here I have two schemes, but these schemes are not bounded. Okay, you can have all sorts of degrees. So here are some notations. Each one of these relative functors admit two subfunctors, which this notation say precisely what they are. The notations are a bit heavy, but you will understand that I need this kind of heavy notation to make myself understood in a second. When I will get to twisted curves, which are stack theoretic curves, these things I'm doing is quite delicate. Okay, so I've seen other people today saying that the line bundles of degree 0, of total degree 0, can be denoted with peak 0 simply. Okay, other people prefer to denote this one with peak 0 simply, because it's the group of the identity components on every fiber. So let's make clear what I mean by these two things and never use peak 0 without underlying. Okay, so here are the line bundles of degree 0 on all components of the fibers. And here are the line bundles of total degree 0. It turns out that for a scheme theoretic curve, this thing is actually the group of the identity components. But you will see for a twisted curve in a second, this thing is no more true. Okay? And that's the whole point of what I'm doing, so I should insist on this. Now comes the theorem. the neuron model of peak 0 k is peak dot 0 r mod the scheme theoretic closure of the 0 section from the generic point. So you have a generic point, you have this type of situation here. You have peak 0 over spec k, which is g-dimensional abelian variety here, the Jacobian. And then of course, you can have a section which is the 0 section. And then you have this scheme, peak dot 0 over r. And the whole point is that this peak dot 0 is everything but bounded. Because if you have a curve which is reducible, then you are only requiring that the degree should be totally 0. But you have, therefore, a large degree of freedom as soon as you have more than one irreducible component. So it's not bounded. Even worse, it's not separated. It's easy to see. Take any irreducible components within a subcurve of the special fiber and consider the line bundle given by twisting by this z. Z is a divisor inside the surface. Okay? So this line bundle restricts to the generic fiber as the trivial line bundle. But it's not trivial on the special fiber. Okay? So here we have a something which is not bounded, not finite type, not separated. Yet, that's the reason why we mod out by this closure of the 0 section. This is what makes the final group scheme bounded and separated, and indeed the neuron model. So to make it more explicit, the 0k closure is indeed the set of line bundles obtained by twisting by divisors where di are subcurves out ck. You take them all. If you want to avoid making useless twistings, avoid those that take the entire special fiber. But then this is what spans this subgroup. This is a flat subgroup. So you can take this quotient, you get another group. And this is precisely what doesn't go very well in this example. You may actually think, naively, to take the same thing. And, well, there are lots of issues that you have to deal with. First of all, these irreducible components may not form a divisor, which is the case here. This is the irreducible component is not something codimension 1. But then one can actually be optimistic about it because Marco has given a talk about these enriched structures, which kind of enlarge this point, and this may actually become a divisor. And then actually, I'd really refer to the paper of David Holmes. I will write his name later because there's going to be a part of my talk in which I illustrate what he does. And he really shows that the analog of this closure of the 0 section is not flat as soon as you have this kind of situations. You characterize them combinatorially. Okay. So well, you have a choice here. We can prove this theorem. I will do it by waving hands. So how do you actually show that this is the neuron model? First of all, at least you should check, and that's all I'm going to do, that every time you have a k point inside here, it extends uniquely to a k point, to r point here. But this is not so difficult because I have assumed that CR is regular. So if I have a line bundle here, it extends to a line bundle here. And this necessarily lives in the PCAR group, which has total degree 0. Finally, the only thing that then I have to check is to control that this is really separated, but it's almost by definition. This operation is what I need, and that it is finite type. And this is just a combinatorial thing. A combinatorial thing which is pleasant And it uses a little bit of this. And it gives us a little break. You can forget of everything I said, and I tell you about this combinatorial thing. Okay? If you want, we just play. It's called the sand pile game, or chip firing game. It has these funny names, and really is the kind of thing you can play with. Take a graph and try to compute the corresponding group. Right. So here it's, I mean, for example, this is the terminology that Dino Lorenzini prefers, and then, sorry, I'm doing this, and then some people therefore call it Laplacian. Others call it the degree class group, which seems to be more related to our problem. And others call it in this funny ways, chip firing, whatever. So what's going on? Well, I think in order to understand what's happening, we have to take, again, this example. This one I've drawn here. A curve getting to this boundary. And now what happens here is that we had a degree 0 line bundle, and we extended it over the entire surface. So we certainly have total degree 0, but not necessarily degree 0 on each component. Okay? But we are actually considering this line bundle up to tensoring as many times as we want with this component I. I called it I because it's the one of the identity element. Okay? So I can take it as many times as I want. And okay, so what is the degree of this line bundle over this special fiber? Well, clearly this has by degree minus 2a on I and 2a on the complement of I closed. Okay? So what happens here is that if I mod out by those guys, I get only two types of classes of equivalence of multi-degrees. I can take the case in which they're both even and the case in which they're both odd. And that's all I get. Okay? So essentially, the connected components of the Néron model of peak 0K special fiber are given by the group Z2Z. Or if you prefer, you can present it as the group we said n minus n mod 2a minus 2a. Okay? Okay, so this immediately makes people figure out what's going on. And this group of connected components in general, it's the group again, I recall it's not difficult to understand that it's exactly that group. First of all, notice that this map goes to C0, and it would form an exact sequence if I just add, after this map, a map that takes the sum of everything that is in C0. This is a zero-valued cochain. I just add up everything. Okay? So this would form an exact sequence, which means that what I get as the image is all the degrees that are totally zero. So precisely the degrees of this guy. So this group reflects precisely the theorem of Renault. And so, of course, what I get here are all the degrees of this guy. And this is a bit more difficult to understand. But just to understand what happens if I take an irreducible component, which is attached to a certain vertex. And this is the vertex attached to Z, the irreducible component. This vertex is linked to many other irreducible components in the dual graph. And maybe there are other components like this, but let me ignore them for a while. And what happens is that twisting by OZ means giving a degree 1 to all the nearby components and subtracting the number of them, here 4, to the degree here. That's the sand pile game. If you think of these vertices as containing some grains of sand, then the moves that you are allowed to play are every time you fix a vertex, just land to all the neighbors a grain of sand. And of course, you lose some grain of sand. The total amount of grains of sand is always the same. Okay, so actually, I don't know, maybe tomorrow I will get to the point of telling you about the twisted curves. And what happens is that essentially these grains of sands are going to be fractioned. Just simply like that, as simple as that. Twisted curves, stacks, allow me more flexibility because I can take these grains and cut them into pieces. So much flexibility that, my theorem is going to look like this. Maybe it's time to announce it to have something that gives us a sense of where we're going. So here it is. Why I gave this title, Neuron Models of P-car Groups by P-car Groups, because I want to write this kind of, how do you say, profanity. Everybody knows that neuron models are not represented by P-car schemes, okay? But I will give a setup in which this turns out to be true. And the advantage of this is that hopefully it will shade some light on this kind of problems that we saw before. Because if you realize the neuron model by a functor, which is nicely behaved, then you maybe have some hope to carry out this construction globally. Okay, so now that I've done my advertisement, which is, as every advertisement, a bit unfair, now let's get back to what is the twisted curves. I have to. So, okay, so maybe you don't like twisted curves. So instead, just compute the group of these graphs. I mean, what I'm trying to say is that it's really amusing to compute this graph, these little groups, the groups that I haven't even tried to give a name to, but I will do it now. And in this case, it's Z3, for example. And there are lots of nice techniques that I learned from Dino Lorenzini, for example. If the graph admits a planar projection, then you can color the regions around and connect them by an edge in this way. And then you form another graph which is dual, and from which is much more easy to prove that the group is Z3. Okay? I mean, these kind of things are a very poor techniques of computations that we can use for these groups, which is highly, well, it's kind of hard to compute, I must say. What else do you know? For example, we know the order of this group. It's classical that it's the number of spanning trees inside the group, inside the graph. Take the graph, draw a spanning tree, a maximal tree inside. There are only 3 ways to do it here, for example, which is taking off this edge, taking off this edge, taking off this edge. Or here, similarly, taking one of this edge only. Okay. Again, hopefully, having introduced these fractional sand piles will actually introduce some more confusion to this computation, and maybe from confusion something good. But okay, so here comes the hero, twisted curves. So again, an example, instead of giving an obscure definition. The example is this. Again, the I, the same curve I used from the very beginning. I have a point here, which is a node. The nodes usually should be looked at as this, but this time I will look at them as a stack. Mu2 is a, well, simple group, so it operates by changing sign to both x and y. Actually, this is an action which has determinant 1. And that's good news, because since it has determinant 1, it can be smoothed. Okay? So the condition that this action is determinant 1 will be kept whenever we speak about these twisted curves. And the reason is that we want to smooth these things. The reason is that we want stacky curves that interact with the usual old curves. Okay? So this is called the balanced twisted curves technically. It was invented by Kontsievich, Abramovich, and Vistoli. And okay, so, well, many things are again the same. For example, the sequence that you usually use to compute the Picard group is still here. So, well, I should have. And it still induces the good old sequence. Let me write with C star. I haven't insisted too much on the fact that I want some generalization in higher, in positive characteristic. So this goes all well. Irreducible components, nodes, peak of C. Here comes a little piece of news. I decided to put the same order of stabilizer everywhere. Here it was 2. In general, I can put L. Okay? Of course, it's not compulsory, and maybe my theorem should be stated more generally. Okay, but you never saw this piece appearing in usual curves. The reason is that here should come the Picard group of a point, and the Picard group of a point is trivial, whereas the Picard group of points nodes here is the set of the group of characters. So since the stabilizer is a mu L, this yields this. Okay, and okay, so then of course you can skip what I will say and work out what the Picard group is there. Or here is an idea. Since we want to finish this talk, and we are interested, as you understood from my first example, in solving the problem of finding square roots of the trivial bundle. You saw this lambda was really annoying us. This lambda that was giving 1 was really the annoying part of the story. So let's just find the square roots of the trivial bundle inside this group. And this is a good thing, because the square roots of the trivial bundle are just the two-folded étale covers. Okay? So let's just find all the two-folded étale covers of this curve. And I tell you in advance, there are 4, and there are not 2 as usually. Usually, when you have such a curve, you have only 2 étale covers. One is the stupid one, in which you just take twice the same thing. And the other is the accordion. Okay? And, but usually you're stuck with that. Whereas with an elliptic curves, you have 4. Here you don't have 4. And this problem is similar to the one I mentioned with the big example with the lambda, et cetera, et cetera. There was this component which was badly behaving. Here we're going to discover points of that components. Okay, so let's see what it is about. Well, it looks like cheating. I'm constructing, okay, so I want to think of this curve as 2 copies of P1, but with a stacky structure. So let Z be the inhomogeneous coordinate, and let mu2 act on the inhomogeneous coordinate by change of sign. This produces stacks here and stacks there. Okay, the parameter on the interior should be regarded as z squared. And now here, I don't actually act with any group. I really take the honest scheme, P1, with the same z. And of course, this as a natural covering, I do the same thing on the other side, and this is a natural covering of my curve. It doesn't look as an étale two-folded cover, of course, but it is because of stacky reasons. I mean, the ramification that you see, that you have the feeling of seeing, is actually just apparent because this point is not actually a single point, but it's a half of a point. It's a stacky point. Okay, so if you look étale locally, this doesn't ramify at all at the node. Okay, and what happens here? Well, I have enough ingredient to tensor two things here and get another thing. Actually, if I had to draw, I would have to draw the same picture. I mean, it doesn't actually show too much on the blackboard, but they are different. Maybe it's better to get back to line bundles now that we have played with curves. Here you have O, disjoint union with O, with the identification given by identifying functions of the same value, essentially. Here you have. But here you can do the same thing and identifying with a -1 here. And here, okay, here comes the interesting part. You have line bundles. Okay, so line bundles are just the old line bundles, Cartier divisors. Okay, so I'm going to specify two Cartier divisors that are two torsion. Okay, so I will call the point lifting this node here P and the point lifting this node Q, and corresponding on this side Q prime and P prime. Then the Cartier divisors are going to be Q prime minus P prime over 2. And then I can glue with a +1 and with a -1. So look at this Cartier divisor. It is not 0, by no means. But if you multiply it by 2, then 2p starts moving in the interior of the curve and meets -2q, and then it becomes trivial. But you have to multiply by 2 for that. So here it's the whole story. Again, if you want to convince yourself of this story, just take one component and not a nodal curve. Unfortunately, it has nothing to do with this talk, but it's a good exercise to understand exactly how this orbifold admits two étale covers. Okay, so well, then I can state this theorem here with recalling in 1 second the setup. So the setup, okay, so the drawback of my approach is that I need to extract square roots like hell, square roots, L roots like hell. So this is not going to be a nice approach if you don't assume that you're in a nice characteristic, okay? So this is the DVR given by extracting an L root from the uniformizer. And okay, so same hypothesis, easy hypothesis that we mentioned before. But this time I want to go on this. And okay, so well, usually one pulls back, but if you pull back, you get a singularity. You pull back, and instead of having xy equal pi, you get pi prime power L. Huh? And this is not going to help you if you want to extend line bundles. But okay, so here is the key ingredient of what I'm going to say today. It's a little bit like the semi-stable minimal regular model. Okay, so in a standard theory of Renault, I haven't mentioned the detail, but Renault deals with the curves that are not forming a regular scheme, but then resolves the singularity, gets a semi-stable curve, which has an interpretation as a universal minimal regular model. Now, here I'm going to do something different. I'm going to realize this local thing by taking x, y, actually L root of this, and this mod mu L. Now, by all means, this is smooth. And if you look at what happened off the origin, it's just isomorphic to what I initially had. So it's just a little surgery. When I take this patch and I don't change anything but the point at the node acquires a stacky structure. And elsewhere, I left everything identical. OK, so here are the corresponding groups. I have my peak 0k. And here, I have the relative peak 0 RL. Now, OK, here comes a really amusing part. Mu L acts on this, of course. It's just a multiplication by psi or whatever. Zeta acts on the parametrizer by the uniformizer by this. Just a multiplication. But this is a mu L equivariant curve. And so the question I'm trying to answer here is, what is this canonical way of lifting this automorphism to this stacky curve? There must be one. Well, it's an automorphism of this little thing that fixes this little thing. And if you think about it, you don't have many choices. And the only way to do it is this. OK? So it doesn't actually sound very correct. I have a privileged x prime, and I've ignored y prime. I'm being unjust to it. And the fact is that it's correct because actions on stacks are always defined up to natural transformations, i.e., they're defined up to the balanced action that I have on here. And the action that I have on here is always balanced, as I said before. It multiplies x by this and and leaves pi unchanged. Okay? So if you change this action by this natural transformation, you just get rid of this and you move it here. So I haven't privileged any branch. And this means that essentially the automorphism groups of the stack theoretic structure relative to the coarse scheme is canonically the number of nodes and mu L. Canonically. So of course, the action that I want is the diagonal. The diagonal is the canonical action I was looking for. And of course, it acts by pullback here. I would like to tell you how, but I cannot. I mean, it's very simple. It has to do with this map here. And, well, I just give you a little hint, and then we have to move on. So here is the theorem. Neural model of this is this. What does it mean that I underline things? I just take off everything in the special fiber that is moved, is not fixed by delta. So it's the peak 0r minus the part of the special fiber that is not fixed, the moving part of the special fiber. OK, so this gives not only this theorem, but it gives something global. And now I'm going to wipe the blackboard. In 5 minutes, I'm going to tell you 3 global approaches, one better than the other. One is David Holmes. The other is Caporaso and Eduardo, I think, because there is some stuff that I've learned during these days. And OK, so each of them fails on one side. On the other side, this neuron beast is really hard to tame. But they all reveal aspects of this. What we're trying to do here is to construct the neuron model over this 2-dimensional basis. So I started from it, and I think it's time to wrap up my talk and get to this neuron basis.
That peak 0r from which you remove any moving part is
Sorry?
actually that one there, right?
Sorry?
Yeah.
Very good. And of course, there is another natural question is, what is the L that you need to choose? I have an L here. Can't you just choose L equal to 1? Well, L can be any multiple of the number of maximal trees if you want. It's the order, or better, the exponents in this. Another thing I have to mention is that, of course, once you have this theorem, you can wonder if you can derive from it a description of the component group. And you get one. It's not the same as before. It's actually radically different. But maybe dual, actually, in this case here, I'm saying it's very easy to see it's dual. But in general, if you let all these groups appearing, you get really maybe some new formula. I don't know. So let's move on to these three approaches. Well, the philosophy for my approach, you got it. You have a moduli space of curves which always carry an L stabilizer. It's a Deligne-Mumford stack. You remove some closed loci on the boundary. You get something which is a proper, sorry, not a proper, it lives in a proper scheme. It's a compactification. And every time you had a spec K and the Jacobian, and you wanted to construct a Néron model on spec R, well, then you are forced to consider this and pull back here and realize that this Néron model is going to be the same thing as this. So it's not just patching together Néron model, but patching together pullbacks of Néron models. So it doesn't patch together Néron model. It patches pullback. But so second, it is a group. And it lives on a proper modification. Of MG bar. So it only glues together pullbacks of Néron models. And here is what David Holmes has done, for which I refer to a paper appeared in December 2014. And I'm going to be not too I should give his theorem in full force, and instead I'm going to just give his theorem in a single example. So what he does is, remember we had this two divisor meeting at one point. We're going to blow up. They're not going to meet anymore. They're going to meet an exceptional curve, just like in the talk of Marco. But then we're going to blow up again. So we're going to have them here. He finds that this is what you have to do if you really want to glue together Néron model. You have to keep on blowing up. That's the point. So here you're going to parameterize the strokes, the traits that come with incidence 1 and 1. Here you're going to parameterize the one that come with incidence 1 and 2. Here you're going to parameterize the one that come with incidence 2 and 1. And again, you can keep on playing this game. You have 3 and 1. You have the fairy sequence here. You have the 3, 2, and the 2, 3, and 1, 3. And the whole point, you never should stop. You should get this unbounded thing. And once you have this unbounded thing, even on the moduli space of curves MG, you have constructed something which is what he calls a universal Néron admitting model. Or maybe no, universal Néron admitting morphisms. He classifies all morphisms on which you can play the Néron, you can install a Néron model. And this is going to be the one through which all of them factor by playing this game, blowing up over and over again. And on top of this, he has a neuron model. This is, and maybe this also calls for a more precise. I mean, I saw this talk and there was Amini who had some interesting remark. Maybe there is some modular interpretation that is possible or already in his paper. Well, okay, so Lucia does something else. Caporazzo takes some special degrees. So this is going to be the universal Picard variety of a certain chosen degree from the very beginning. Say that degree is 1 for simplicity. Why didn't I choose 0? You will see in a minute. In the case of peak CK, you can actually obtain the right answer by gluing together along K two Picard functors that are the one where the degree on this I curve is 0 and 1, and the one that is 1 and 0. This is better than with 0. With 0, you had to do 0, 0, and 1, and minus 1. And the question you were asking yourself is which one I should call 1 and which one I could call minus 1. But here I don't need that. The thing is that I have to deal with the degree 1 thing. And Eduardo has actually a machine that selects this thing. I mean, there is this sets of equations, inequalities, which is strongly balanced conditions. Okay, so, and in this approach here, finally, how does that solve the problem? Well, in this approach, you can consider that all line bundles have degree 0. But once you do it with character 0 and character 0 here, and once you do it with character 1 here, which are, if you remember, still the 4 covers that I have mentioned. 2 of them were of this kind, and 2 of them were of this kind. So, okay, as you see, this allows to solve the problem with degree 0 without making any choice, because I didn't have to privilege any node on any, or any component. And, you know, since these neuron models are just the first, you know, when you have this construction with paper that you do with kids, and you have to glue, so put some glue here, and it's indicated where you have to, what you have to glue to the other things. And Lucia has a paper saying that you can compactify by gluing neuron models like this. So having a nice way of interpreting the neuron model is probably the first step to assemble them and compactify them together. And of course, then computing quantum invariance of BC star and such things. Thank you very much.